Welcome back, everyone. In this section, we are going to start talking about inverse trigonometric functions. Just like in Chapter 6, we introduced exponential functions, then we had to talk about the inverse of exponential functions so that we could solve exponential equations. Similarly, we've introduced trigonometric functions, and we're going to need to talk about an inverse to those functions if we want to solve trigonometric equations. Now, we run into a problem right away, which is if you're looking for the inverse of any function, you only have an inverse if your function is one-to-one. And remember that a one-to-one function is one where any horizontal line crosses through the graph in at most one place. So just to flash back to previous material, if I gave you the graph of y equals x cubed, that is one-to-one because any horizontal line you feel like drawing certainly will cross through the graph in at most one place. On the other hand, if you were to look at the graph of y equals x squared, that wouldn't be one-to-one because a horizontal line can cross through that graph in more than one place. Now, the problem is, of course, because all of our trig functions are periodic, then that means that they use every y value more than once. The sine function, for example, even in just one cycle, goes through the same y values twice. It passes through those y values twice. It passes through those y values twice. So the plan is that we won't be able to define an inverse trig function for sine using its whole domain. Instead, what we're going to do is restrict our domain. We'll say, well, instead of taking sine defined for all real numbers, we'll define sine on a smaller interval where it is one-to-one, and then we'll be able to have an inverse function just on that little restricted domain. So the domain that we'll work with for sine is negative pi over 2 to pi over 2, or negative 90 to 90. And if you're thinking about which quadrants those are, from negative 90, which is down there, up to 90, which is there, those would be quadrants 1 and 4. And the reason why we're going with quadrants 1 and 4, remember that in quadrant 1, sine would be positive, and in quadrant 4, cosine is positive, which means sine would be negative. In other words, we have one quadrant that's going to give us our positive values for sine, and one quadrant that's going to give us our negative values for sine. So in between negative pi over 2 and pi over 2, sine will go through its whole range of possible y values from negative 1 to 1. The notation that we use here is similar to the notation that we used for other inverses. If you're remembering back in Chapter 6, when we wanted to talk about the inverse of f of x, we would write f with the little -1, and that would be the inverse of f. It wasn't an exponent. This wasn't the reciprocal of f. It was the inverse. Similarly here for sine, to talk about the inverse, I'll write sine with a little -1 x. Again, that -1 is not a power. This is not the reciprocal of sine. This is the inverse of sine. Another name that we have for the inverse sine function is arcsine. So you might see, for example, y equals arcsine of x. But those two things are exactly the same. Arcsine of x is exactly the same thing as sine inverse of x. They're just different notations for exactly the same thing. And we kind of have to get used to seeing things written in multiple ways. So throughout, I'll sometimes say sine inverse, and sometimes I'll say arcsine, just to keep it exciting. So the whole idea here is, just as always, if we're talking about an inverse function, it's exchanging the input and the output. So here, you know, for example, if you're using your special triangles, if we were talking about y equals sine of x, if you had an input of pi over 6, or 30 degrees, then the output that you get would be a half. So for the inverse, it'll switch that. Instead of having 30 degrees being the input, it'll have 30 degrees, or rather pi over 6, being the output. And instead of a half being the output, a half will be the input. Another way of thinking about it here would be, or writing it rather, would be this example. And this makes the input-output exchange even clearer. For the function sine, if we put pi over 4 as the input, 45 degrees, we get root 2 over 2 as the output. And for sine inverse, it just switches the input and the output. So for sine inverse, instead of root 2 over 2 being the output, root 2 over 2 instead is the input for sine inverse. And instead of pi over 4 being the input, pi over 4 is the output. So if we're thinking about graphing, the graph for our sine function, if we restrict it from negative pi over 2 to pi over 2, we just have this little chunk that we have here stretching from as low as -1 to as high as +1. So for sine of x in that little restricted domain, the range is from -1 to +1, and the domain was from negative pi over 2 to pi over 2. And remember, for inverse functions, everything is switched, domains and ranges. So whatever was the domain for the sine function becomes the range for the inverse sine function. And similarly, the range for the sine function is the domain of inverse sine. That also means that on the graph, the points are being switched as well. So for example, if you're thinking about this point that I have right over here at the top, if I were to label its coordinates, that's pi over 2, comma 1. So when x is pi over 2, the y value is 1. Equivalently, on the inverse graph, we have the point 1 pi over 2. When x is 1 for sine inverse, then the y value is pi over 2. And if we're thinking just sort of in general, what are these functions doing? Who are their inputs and who are their outputs? Remember, for the sine function, you're putting an angle in as the input, an angle between negative pi over 2 and pi over 2. That means for sine inverse, the output will be an angle between negative pi over 2 and pi over 2. The sine function has an output between -1 and 1, which means the sine inverse function has an input between -1 and 1. So for finding the inverse sine functions, remember first off, the way that we defined our sine function was with a domain in terms of radians, negative pi over 2 to pi over 2. Which means the output for inverse sine functions will be an angle also in terms of radians. So that's the first thing to be clear here. When we're giving our angles, whether it's for sine or for sine inverse, we will exclusively be using radians here. For a lot of the angles that I'll be looking at, we'll be able to, with our special triangles, find the exact value of those inverse trig functions. There will be some cases where we won't be able to, in which case we'll use our calculators to give us some approximate values. But as always, unless I ask you for a rounded off approximate calculator value, I really want the exact value of trig functions or inverse trig functions. So for the first one, we want to find sine inverse of a half. And I'm just going to quickly jot down my special triangle here for the 30, 60, 90. And I'm going to write it in terms of radians to keep things exciting. So 30 degrees, that would be pi over 6. 60 degrees, that would be pi over 3. Opposite the 30-degree angle, so opposite pi over 6, the side length is 1. Opposite the pi over 3 or 60-degree angle, the side length is root 3. And opposite the hypotenuse, the side length is 2. Now, if we were thinking about our special triangles, we could say, well, if you were looking at, for example, pi over 6 or 30 degrees, sine of that would be opposite over hypotenuse, 1 over 2. So we know that sine of pi over 6 is opposite over hypotenuse, or 1 over 2. So that means sine inverse will switch those inputs and outputs. Instead of 1/2 being the output, 1/2 will be the input. Instead of pi over 6 being the input, pi over 6 will be the output. So the answer to our question of what is the inverse sine of a half, inverse sine of a half is pi over 6. The reason why it's pi over 6 is because sine of pi over 6 is a half. Let's do another example. Sine inverse of -1. And if you're thinking back to the graph that we had just looked at, we know on the sine graph that the y value of -1 happens when the x value is -π/2. So the one thing that I know, if I were to summarize that, I could say, well, I know that sine of -π/2 is -1. And if that's the case, then that means for sine inverse, it will switch the inputs and the outputs. So instead of having -1 as the output, we have -1 as the input. And instead of having -π/2 as the input, we'll have -π/2 as the output. So sine inverse of -1 is -π/2. All right, one more. Arcsine of -√3/2. Arcsine, of course, that's the same thing as saying sine inverse of -√3/2. And if we go back to our special triangle for just a minute, for 60 degrees, we can see that for 60 degrees, or π/3, sine of π/3 would be opposite over hypotenuse, which is √3/2. So going back, if we say to ourselves, well, we know that sine of π/3 is √3/2, well, then we know that sine of -π/3 should be -√3/2. And the reason I know that, of course, is because if we're thinking about our quadrants, π/3, that's in quadrant 1 where sine is positive and has reference angle π/3. And if we're thinking about -π/3, that's in quadrant 4, and its reference angle is also π/3. So sine of π/3 and sine of -π/3, they've got opposite signs, because in quadrant 4, if we're thinking about our cast rule, all students take calculus, in quadrant 4 it's cosine that's positive and sine is negative. So what do we have? We can now say that since sine of -π/3 is -√3/2, then that means sine inverse of -√3/2 is -π/3. All right, excellent. Let's do one more. Now, before we do that, this will be a calculator example, and this is where we'll point out a couple of things on our calculator yet again. The first is a reminder from before that the button that we see here, the DRG button, that's the button that we'll need to press to turn our calculator into radians mode. Right now in this image, you can see up top it says DEG. My calculator is currently set to degrees. Every time you push the DRG button, it will change what it says at the top from degrees to radians to gradians. Because inverse trig functions are defined to give their output in terms of radians, then we need to have our calculator set to radians mode. For the inverse trig functions, you can see that they live right here above the trig functions. There's inverse sine, there's inverse cosine, and there's inverse tangent. And to get at all of them, we just need to use the second function button that we have in this corner. So if we wanted to enter, for example, what is sine inverse of -1, you would have to enter second function, sine inverse, and then -1, and then equals. So let's do an example. We are looking for the approximate value of sine inverse of 7/10. So since we want the approximate value, then I know I'm fine to use my calculator. And in fact, if I'm thinking about my special triangles, I know that 7/10 is not one of the values that I would ever get from one of my special triangles. I'll get halves and √3/2s and √2/2s for my sine function, but there's no way I would get a 7/10. So we will use our calculator, and if we want to find sine inverse of 7/10, then in our calculator, first off, making sure that we are in the right mode, making sure that it says radians and not degrees. Right now it says degrees, so we would need to push the DRG button as many times as it takes to make it say radians at the top, RAD. Once we have that, then I would enter exactly what I want. I want sine inverse, so second function sine inverse, and then I want 7/10, so 7 fraction 10, and hit equals. And once I do that, I will let you take a second to put that into your calculator. But once you do that, I found that my approximate value was about 0.775397, thereabouts. So rounded to 3 decimal places, I have sine inverse of 7/10 being about 0.775. And if I wanted to give units with this, I could say RAD, radians, just to make it really clear that my output is radians. This is not 0.775 degrees, it's 0.775 radians. Okay, so we'll have ourselves a brief pause, and when we come back, we're going to talk about composing the sine function with the inverse sine function, which is an interesting little topic. And we'll also introduce inverse cosine functions in the next part of the lecture. Okay, so take yourself a break, make yourself a cup of tea, and we will see you all in a few minutes.